So I'm going to go ahead and start recording. You guys at home, let's see here. Are you getting my full screen or just the PowerPoint at home?
The full PowerPoint.
So you're not seeing my presenter view, right?
No, we're seeing the full PowerPoint.
Okay, great. So, well, maybe not great. It's just happening. Slight reprieve. Okay, cool. So for you guys at home, again, if you have a question or anything like that, make sure you speak up. I'm not going to be checking the chat. I'm not going to be looking for any of the emojis or anything like that. If I don't hear you, I won't know that you have got a question or anything. Otherwise, it's nice to see you guys again. Last time we had a talk, I introduced you guys to some of the foundational knowledge that you need to use Unix systems. You use the shell, you use the command line, various terms that are associated with that, right? And my idea with that sort of approach, PowerPoint's going to keep crapping out on me here, is just really that as bioinformaticians, you guys are going to be using computers all the time, right? You're largely data scientists, applied data scientists. And I know that most of you don't have a background in computer science. So today, is another one of these talks where I'm hoping you guys will put on your computer scientist hat for the day, and you'll get exposed to some more of this information that really makes bioinformatics possible and largely will allow you to do more work, bioinformatically speaking, without being constrained by tools that are available. It can also allow you to use other tools that maybe you wouldn't be so comfortable using because they're command line based or things like that. So I'm going to start the slide here instead. I think sometimes my little videos crash things out for some reason. Okay, so I like to just start with the definition of programming. It's a good place to start, right? How many of you guys have any programming experience at all? Any of you? A little bit? Decent amount? Okay, cool. So programming is a pretty straightforward definition, but I've pulled 3 different definitions here for you guys, and so I'm going to just read these off the screen for once. The process or activity of writing computer programs, straightforward, right? The process of designing and building an executable computer program to accomplish a specific computing result or to perform a specific task. Oh, that's kind of a verbose way of just saying the top one, but that's another way to say it. The implementation of logic to facilitate specified computing operations and functionality. Well, I like that one the most, personally. I think it's pretty well said. I think the terms are really good here, especially with an emphasis on logic, because when you think about programming, no matter what language you decide to program in, you always need to know what programming logic is. Programming logic is ubiquitous. It doesn't matter the language. The logic is always going to be the same. Bear with me. If this thing keeps crashing, I might have to go in and edit the PowerPoint real quick. Something about Teams in my PowerPoints. I had this issue last time, didn't I? One of my slides were crashing on the videos. I need to remember that. Okay, so if that's the definition, then let's start talking about programming languages. But before I really talk about programming languages, I tend to start with computer hardware generation, right? So the reason that programming language exists is because computers exist, right? Without one, you don't have a need for the other. And differences in programming languages over the years and the development of new programming languages over the years goes hand in hand with the development of new computer hardware technology, right? And so if you guys have never seen these items before, welcome to the kind of the fundamental units of computing, right? If you go way back in time, you get vacuum tubes. The vacuum tubes allow you to control the electrons in the vacuum chamber. You can use a vacuum tube as a switch, as an amplifier for various activities. But in the context of building a computer, you would use it as a switch. Okay, I really like using an analogy in my head when I think about how these things operate as switches. And I just picture a water tower. And I picture the water tower either is full of water or is empty, right? And in that way, you can think of a vacuum tube as either having a vacuum or not having a vacuum. You can think of something that's electronic as either having a charge or not having a charge. Bear with me. I'm going to take just a moment real quick and see if I delete all of this stuff out of the PowerPoint if it stops crashing on us. Or actually, why don't I just fall back on a PDF? Oh, I really don't want to do that. Yeah, bear with me a second. Or more like bear with me for 2 minutes. Wonder how many times I have to do this. Oh, too many times. It's a bummer. Whatever, I'll just keep pushing through it for now. Sorry. I'll go to the PDF in a minute, but then the presentation style gets kind of weird. Okay, so we have different computer hardware. Vacuum tubes were the initial measure, and this is kind of interesting. Actually, in the automotive industry, we used to use vacuum as a signal for a lot of things automotively, to control your air conditioning, control your carburetor, various things like that. But eventually, those technologies were replaced with electronics, with wire. And that's the same case for regular computers as we think about them. So transistors replace vacuum tubes in functionality. Transistors operate in a similar. And the idea is that these transistors either have a charge or they don't have a charge. And then as such, they can be used to, again, amplify signals. They can be used to serve as switches and so on and so forth. As we continue to build more advanced computers over time, we needed more transistors. And inevitably, what we ended up designing were these things called integrated circuits. So integrated circuits are, okay, we'll go to the PDF. Integrated circuits are just a dedicated chip with numerous transistors on it. Okay, so instead of just one transistor, you have hundreds, maybe thousands of transistors on one of these things. Oh, my clicker's going to work. Okay, it won't be that bad. Cool. So integrated circuits, natural progression off of a single transistor to allow you to have a lot of tiny transistors in a small spot so that you can do more computing. These things are what really give you computing power. Fast forward in time a little bit, integrated circuits aren't getting as much performance that we might want at a given time, and so we invent microprocessors. Microprocessors, just like going from a transistor to an integrated circuit, is largely this idea of miniaturizing and amplifying the number of components on a single piece of hardware. And in this case, you can think of a microprocessor as kind of containing numerous integrated circuits is a decent way to at least think about it. The general theme here is that as we're moving, we're increasing the density of the transistors, the density of our compute capability, which is a direct function of the number of these transistors that are inevitably somewhere buried within our hardware. Now, we fast forward into modern day, into today. I'm sure you guys have heard about GPUs, graphical processing units, right? If you're a gamer, you know all about it. If you're into machine learning, and they're at the heart of so many machine learning processes. If you guys, all of the modern phones today largely have GPUs in them and all sorts of stuff like that. So GPUs and other chipsets like this, they take on this idea again, but instead of having a single microprocessor, a parallel processing chip like a GPU or a multi-core CPU is going to have numerous microprocessors incorporated under a single device. It makes pretty good sense, right? Nice logical kind of progression, okay? Well, as a result of this, there's also numerous generations of programming languages. We go all the way back to the very beginning. The first generation of programming languages are considered machine-level languages. Very difficult for humans to look at and interpret and read. because they are literally written as a raw instruction set for these transistors. Okay, so when you see zeros and ones, what I want you to think about, if you're using my water tower analogy, is that a zero tells the computer that's an empty transistor, it's an empty water tower, and a one says, hey, this thing's full of water. Okay, right? So this is a way that the computer can do something physically, right? It has these real transistors, they really have a charge on them, or they really don't. And we can look and interpret the pattern of those charges to do something meaningful with that, right? And so machine level languages are still actually used today, they're just hidden from us. Everything that we implement in any other programming language inevitably needs to be processed by the hardware, and it is inevitably converted to machine level code. Okay. We improved on this over time. As you can imagine, the very first generation of programmers probably didn't love their job. I'm sure they did, but they didn't know how good it could eventually get. Well, they improved upon this by introducing what are known as assembly languages. So assembly languages start to become much more human-friendly, right? You can look at this, you can kind of get a sense of what's happening here. I know it's a little washed out on the slide in the classroom here, but here they're going through, they're declaring a variable, initializing it to a value, and they're looping and doing some iterative process with these, right? And so this assembly language makes writing codes and instructing computers so much simpler than directly writing machine level language. But again, this ultimately gets converted to machine level code to be processed, okay? Let me also throw in an extra bit here, is that the machine level code is specific to specific hardware, okay? One machine doesn't necessarily use the same form as another machine. Bits in terms of how it's storing and using that information, in terms of its architecture, if you hear this term, computer architecture. This is why there is a lot of pushback. Apple notebooks are notorious for not being well suited for the gaming community. There's games that don't work. And oftentimes when you have software incompatibilities such as that, that arises from the fact that the code has been written in such a way that it's only converted into machine level languages for specific hardware. And oftentimes that will be something like Microsoft systems and things like that. We go a little bit further in time and we get machine independent languages. These are great. My favorite languages are machine independent languages personally. We still use these all the time today. An example of this is the programming language C, right? C++ is another example of this. These are considered machine independent because I can write a set of instructions, I can develop a program in this language, and I can compile that program to run on any computer, right? There's an extra step in the process now that there's a compiler introduced into the pipeline that takes the code I've written in a machine-independent fashion, and it knows how to convert it to a machine level appropriate for a given piece of hardware, right? This is really nice because back in the 50s, late 50s, early 60s and 70s, when you wrote a code, you wrote it for a specific computer, okay? And if you wanted to go run that code on a different computer, good luck. You got to go write another program. You got to rewrite it, right? It's no fun. We get a little more advanced. Have you guys ever heard of a language called SQL, SQL? Structured Query Language. Yeah. So this is a language that's used for manipulating and designing databases and things like that. And this is considered a program generating language. So as we continue to move to the left here, which signifies moving forward in time, what's happening with the computer programming languages that you're removing yourself further and further and further away from considering the hardware, right? When you're writing machine level language, you have to absolutely know the hardware because you're writing raw machine level instructions. Moving to assembly, at least now we're typing in a language of our choice, not just typing ones and zeros. We get all the way up to program generating languages, and these languages are kind of abstracting, as we would say, abstracting away some of the actual implementation in terms of the instructions. We're providing things like select, group by, order by. And SQL is just designed as a language to perform certain operations based on these commands, right? We can go even further. And we have what are known as problem-solving languages. These languages fit into what's called declarative programming, which I'll touch on a little bit, but It's quite niche. Not many people, at least in the mainstream, do this kind of programming. But these languages are well suited for problems where instead of telling the computer how to solve a problem, let's think of a function where I ask a program, if I give you an x-intercept and I give you a slope, right? Give me the equation of the line or something like that. That's a very straightforward algorithm. But what if I give a program just a random problem and I ask it to solve it without telling it exactly how to solve that problem, and I leave it up to the program and the way that the language is written to arrive at a solution? It's a weird way of thinking when you're used to thinking about computer programming in the more canonical way, as I might describe it. But they do exist. Now, we use a bit of jargon when we talk about programming languages, and I refer to this quite a bit when I talk to folks about being high level and low level. Okay? A low level programming language is a language that is close to the hardware in terms of your thinking as a programmer. The lower level the programming language, the more knowledgeable you have to be about the system that you're using, the more careful you need to be about the resources on the computer that you're using, because you have direct control over those things. As you move to higher level languages, your focus on the underlying hardware is alleviated by the software itself, by the programming language, right? And so I get up to a point, taking SQL again as an example here, right? And I can use a statement like select, right? When I'm saying select the Department of Energy or whatever, I'm not really thinking in terms of programming at all when I make that statement, am I? Yet, SQL still facilitates this process by converting these lines into some sort of machine-independent language underneath, which is why it's called program generating, because these commands ultimately generate machine-independent code underneath, okay? And we go forward. So high level, low level. If you guys are ever hearing this term, that's what it's referring to. A higher level language just means further abstracted away from thinking about the hardware. So what's the most prominent programming languages that we use today? I know I just showed you guys these 5 generations, 1, 2, 3, 4, 5. Any guesses? You nailed it. It's 3 and 4. Absolutely, right? That 5th generation language, those problem solving languages are quite niche. Maybe they're more involved in more computer science research and things like that, right? Not so much in the application realm like bioinformatics. And of course, 4th generation is very popular because program generating languages like SQL are extremely useful, and they're easy to move into and be productive with rapidly without having to learn a bunch of underpinnings of programming language, like you might have to do with something like C or C++. So here's some examples of some of these languages. Examples that I think you might come across, you might be exposed to or hear about in this class and other classes. 3rd generation languages, Fortran. It's a numerical programming language. It's one of the oldest programming languages. And if you're trying to do nothing but raw math, it's an exceptional programming language to use for numerical computations. It's very fast. C, C++, C#. Hopefully by now you guys have at least heard about C or one of its family members. Extremely powerful languages, and personally for me, C is arguably the best programming language that has ever existed. Maybe ever will. I don't know this. You've probably heard of Java, or you'll hear of Java. Java's been around for quite some time, and it's heavily used in industry. So one of the reasons Java has so much sticking power, and it hasn't been supplanted by a more modern language, maybe something like a Python, is because a lot of companies have invested a lot of money in the past into developing infrastructure within their companies that are written in Java. And it would take a lot of money and a lot of time to rewrite those things in a newer language. So they just continue to hire Java developers to continue to modify and maintain these pieces of software. I think that's kind of interesting. Python is another great example, and I'm sure you guys have seen Python, heard of Python. It's probably the fastest growing programming language in terms of usage for the last 4 or 5 years now. I think every year when you look at it, Python just continues to grow in popularity. It's very easy to get started with Python. There's a lot of very well-developed libraries for Python that allow you to do complex operations without having to implement those operations on your own up front. Okay, so if you're trying to do a lot of math or linear algebra or calculus, right, you don't have to worry about writing these mathematical functions. You can rely on a package that Python has like NumPy, which has all of this stuff already implemented. You know that it's going to be correct when you get an answer out of it. And you think about the fourth generation languages. I've already mentioned SQL to you guys for databases. There's R. I'm sure you've all heard of R. People love talking about R in bioinformatics. R is a statistical programming language. And if you want to be very technical, R is not a programming language. R is a framework that rests on top of a programming language called S. So if you want to be really technical, you can get somebody with that. But you'll see in the community, R is referred to quite a bit as a programming language, despite that. There's also MATLAB, another popular one I'm sure you guys have heard about or will come across. MATLAB's similar to something like Python, where you can kind of get it really quickly and do some meaningful work and get some results out. But let me always remind you of something, that as you find a language provides you with additional conveniences, you have to know that there's a cost for those conveniences. Oftentimes, that cost is performance. So given your exercise or whatever application you may have when you're deciding what programming language you may choose to use, if you're going to try to write a program, if performance is not a concern for you, then by all means, picking something like a Python or like R, something that allows you to get it very quickly and to get things done is going to be great. And if you're ever in a position where you need performance, let's say you're dealing with an extremely large data set, maybe you've downloaded every genome available to man, right? Maybe you want to do some intense numerical computations on this data set. Well, if you don't want to sit around for a couple months while the computer crunches numbers, you may want to decide to write that in a language like C or Fortran instead, where the additional time is put on the programmer in order to make the program run exceedingly fast. Okay. So how do we convert source code into an actual executable program? Who knows? Well,
Convert it into bytecode.
what's that?
Convert it into bytecode.
Okay, what converts it? I'm sure you guys know the word.
Interpret.
The interpreter is absolutely one of two answers I'm looking for. I'm looking for one other. So if you're not interpreting, you're doing something else. Compiler. You guys got it, right? So compilers or interpreters. And the reason I'm introducing this to you is because I want you to know that there really are two paradigms when it comes to programming languages. They're either referred to as an interpreted programming language, or they're referred to as a compiled programming language. Okay? I'm pretty sure I've got some examples here. So what's the difference here? Well, for a language like Fortran or C or even Java for that matter, when I write the code, I have to pass it through a program that is part of the programming language called the compiler. That compiler converts what I've written as code into the bytecode, which inevitably is down processed at some point to machine level code and actually executes instructions on a system point, right? But you can't execute the source code, right? When you're dealing with compiled language, source code is an instruction set, not something functional. Okay? Again, keep in mind that I'm telling you about there's gives and takes, right? So if I have to spend extra time compiling over here, well, that kind of suggests that maybe these languages are a little faster because they're pre-compiled. Okay? And in fact, that is the case. Oftentimes, languages that are compiled do run quicker than an interpreted language. So we look at interpreted languages. SQL, R, MATLAB, Python. These are all interpreted languages. And so what's really happening with an interpreted language is you're kind of compiling on the fly, so to say, right? You're doing it at each keystroke when you hit enter. That one line of code is being immediately compiled and processed immediately. Now, you can take an interpreted language and you can put all the source code you want into a file. You can refer to that as a Python program, or you can refer to it as a Python script. Either term is okay. And because the language interprets line by line by line, you can pass an entire instruction set, that script or that program, to the interpreter, and it will run as though it were a precompiled program. Even though you get the sense that it's running like a precompiled program, it is still being processed and interpreted line by line. Okay? That's the big takeaway. Two different paradigms, interpreted or compiled. Well, some of these languages actually do a little bit of both, right? And so Java, Python, SQL, just to be technically correct for you guys, I've included this. There's a little bit of both. So sometimes certain parts do get compiled, but other parts are interpreted. It's okay, though, to just stick with this notion of interpreted versus compiled. That's a really good place to start, and that's going to allow you to understand most languages off the get-go. So I've mentioned this word abstract or abstraction maybe now once or two times since I started talking. And so what is abstraction? Well, abstraction in programming is not this, right? It's not art, so to say. It's this idea that when you're programming and you're writing instructions, you don't want to repeat yourself, right? That's wasted time. So if you can think about levels of abstraction, as we refer to them, as different levels of what you're writing that don't really need to be aware of the other levels. So let's say I'm going to write some code that does some math. Maybe it does like some pretty advanced math. And part of this advanced math is that I need to compute a square root of numbers. Maybe I need to compute the magnitude of a three-dimensional vector, okay? Which would also require taking the square root, right? Well, instead of throughout my code constantly writing the instructions to do square roots over and over and over again, to have to write how to get the magnitude of a vector over and over and over again, wouldn't it make sense for me to define a single function, square root, or maybe a single function magnitude, to write the instructions for that operation therein, and then in the rest of my code, I just always reference that one function, right? Now, instead of constantly rewriting the same instructions everywhere, I've abstracted that away, right? I've alleviated myself from having to be concerned with throughout the rest of the code because now I know that, hey, there's just a square root function I wrote and I can use that everywhere. Right? So this is a good principle. When you're writing code, try to get into a position that you're not just repeating yourself. So don't get me wrong, if you haven't ever spent a lot of time writing code in the past, sometimes these tips come with experience. Sometimes it's enough to just get going, to just get a result. And you don't care how ugly, how crude, how inefficient the code might look, because when you run it, you get the right answer and you get an answer. And that's what's most important. What will happen to you over time is that if you find yourself writing code significantly and often, you'll be like, man, I'm being really inefficient. How can I stop wasting my own time? I'm tired of repeating this over and over again. And you'll start to see value in things like the abstraction principle. It's why it's taught up front in programming, because it's really considered a best practice. If you can adopt this principle from programming or in programming from the get-go, you'll be better off than most. So, got a little review here because I feel like the information is probably very new for most of you, and I tend to put a lot of information here. So let's go over this real quick before we kind of switch gears. So how many generations of computer hardware did I show you guys exist? You remember? 5, absolutely. Okay. And how many generations of programming languages? There's also 5, absolutely, right? That makes sense. The languages kind of correspond with the hardware. Most programming, the more programmer-friendly languages are high level or low level? High level. Good. What level languages have less what? See, this one's a more challenging question. Low-level languages have less what? Absolutely, you nailed it. Awesome. All right? So this kind of makes sense, right? It's a lower level. I'm thinking more about the hardware, and so I've abstracted less away. And that makes sense again with the definition of abstraction in terms of not thinking about certain things, right? So that all kind of lines up. And then high-level languages in particular. So when I say high-level languages here, I'm talking about not machine level and not assembly, things higher than that. They can be what or what? Excellent. They can be either compiled or interpreted. Absolutely, you got it. Great.
Hey, guy, I have a question.
Sure.
Whether HTML5 fall within this level.
Where does what?
HTML5, the programming language for writing website.
HTML is not a programming language.
Oh,
It's a markup language.
what kind? Oh, okay.
Yeah. Yeah. There's actually a lot of jokes if you get on like groups with computer science memes. There's all sorts of jokes about people thinking HTML is a programming language. It's funny. You're included in that now, Sam. I'm just messing with you. Okay. So finally, low-level languages are what? So what happens once we have this low-level language? How does it actually get to the point where we can process it? Close, very close. So the term we actually use, and I didn't give you this term, so I was kind of playing with you a little bit here, is assembly. Okay? Once we go from that part there, that's considered the assembly part, which is why those are called assembly languages. They still exist underneath a lot of things. Great. So let's go over some programming paradigms now. And when I'm saying programming paradigms, don't get these confused with two paradigms of programming languages, which were the ones I just gave you in terms of compiled and interpreted. This is different. This is ways to approach a problem that you're wanting to program. Okay? That's what I mean here with these paradigms. So there's imperative and there's declarative. These are the two big branches that you'll see. And I think I hinted at declarative earlier, right? That's the one that we'll touch on. But if there's something you forget today, it can be the declarative programming stuff and the problem-solving language. So the big difference here, right? And imperative and declarative, if you look up the definition, it kind of tells you exactly what the difference is. Imperative tells you how to accomplish a given task. Declarative tells you what you want to accomplish. Right? So this is why problem-solving programming languages are declarative, because you're just telling them what you want to happen, not how to do it. So let's think about a couple examples I have here. A cookbook recipe, is it declarative or imperative? Imperative. All right. What about turn left? Imperative or declarative statement? It's imperative. Okay. How about an equation? Just a mathematical equation. Is a mathematical equation imperative or declarative? Imperative. Okay. She's hungry. Declarative, right? I'm not telling you how to sate that hunger. Just letting you know there's a problem here. Okay, cool. Table for two. Declarative. Good. So when we focus in on imperative, what we see is two big paradigms within this paradigm. And these are the two that I think most students should be exposed to and should be a little familiar with. Okay? That's procedural programming and object-oriented programming. The biggest difference between the two is that when you're thinking in terms of object-oriented programming, you're thinking in terms of your familiarity with the real world, right? I think we can all agree that if I try to invoke the mental image in all of you of a vehicle, we can all get there, right? We all can picture a vehicle. And if I were to ask you guys what some common properties of a vehicle, I can even be more specific. I'll say, what about a minivan? We can picture that minivan. And I'll ask you guys, what are some functions of minivans? Well, most of us might say they're going to have probably some sort of door on the side. Maybe it slides, maybe it doesn't, right? It's going to have a driver door, probably a passenger door, windows, gas tank, fuel cell, battery, if it's like a Tesla or something, right? This idea that you have a class of objects like vehicle, maybe a subclass of vehicle called van, and that every single van has certain attributes, right? So when you're doing object-oriented programming, you're really thinking about your problem and what you're trying to overcome with the code in terms of objects, which can be really natural for programmers to do. That's why programming languages like C++ and Python are so popular, because of the ease in terms of the programmer thinking about how they're writing stuff. I think I put it here, yeah, based on the real world, program divided into objects, right? I give you an example, Python, already mentioned, C++, C# is another object-oriented, Java, Ruby. Honestly, most of the more prevalent popular languages today are all object-oriented. Okay. On the other side of this, you have procedural. So procedural is pretty much reading a cookbook. It's top to bottom, in order. This is how you do it. Procedural is really more of implementing directly an algorithm, right? When we think about an algorithm, we can write down the steps in that algorithm. Maybe step 5 says, if not done, go back to step 2 and repeat, right? But it's still, we've written all those instructions in a sequential manner, and that code is executed sequentially. So C, of course, I'm going to mention C everywhere I can. C is a procedural programming language. Fortran is sequential. What you'll notice here, if you compare these two languages and you have any knowledge about when they were released to the public, these are all newer than these are, right? Procedural languages were awesome for quite some time until object-oriented came about, and they're still awesome, but object-oriented reaches a lot larger community. It's a lot more accessible to more people in terms of how they think about what they're implementing based on Unreal World. I don't know, I think algorithms are in the real world too. Anyways, declarative also breaks down into some sub-paradigms. And so I felt I should at least include this in here once so you see it. There's functional programming. This is very mathematical in nature in terms of how these codes are considered. Literally, your code is a series of mathematical functions constantly operating on one another. You also have logical programming, where you define a set of rules. And based on what you give it, using the sets of rules and the facts, the knowledge that you've established in the code, it's kind of like when you drop a coin in the top of one of those things that, I forget the name, you know, and you try to catch it on the bottom. Right? So if I say where all the pegs are, I say how heavy my coin is, maybe I can use a program to simulate where that's going to land. That would be more like this logic-based. And these are programming languages that I would not be surprised if none of you guys have ever heard about before. With the exception of SQL, Scala, Haskell, Prolog, Mercury, oh my, like what are these things? Well, largely, I don't think you're going to need them, but if you ever do, maybe you've been exposed to them at least. Here's the full chart, breaking it all out. So I did ignore one, which was the mathematical, because to me, it's kind of a subset of that functional and married to it. But this is just a nice overview. You have programming paradigms. They break down into imperative, how to do it, versus declarative, what we want to have done. And then there's ways to achieve these. Procedural or object-oriented for imperative, functional, logic, and mathematical for declarative. So now I've kind of primed you guys, right? I've introduced you to different generations of programming languages, how that corresponds with the hardware. We've introduced some jargon. We've considered that there are programming paradigms, right? There's ways to approach a programming problem to begin with, so we can jump into the basics finally. Well, how do you write a program? What are the 3 steps? If I was going to reduce everything to 3 steps, anyone want to take a stab at this? Okay, well, I'll tell you number 1 is planning. Right? I should always plan my code. This is kind of like trying to write your final essay without outlining it. Don't do that. Highly don't recommend. You should outline always. So planning and programming is like outlining to write an actual essay, right? It establishes a strong skeleton, sets you up for success and efficiency while you're actually writing that code, so you're not wasting your own time. Okay? Well, once we've planned it, we need to implement it. We need to actually write that code. Okay, so that's referred to as implementation. So let's say I've planned something and I've implemented it. What might that last piece be? Any ideas, any guesses? Almost. Kind of. You got it. Testing. All right. I want to make sure it's doing what I expect it to be doing. Okay. If I'm hired by a company to do analysis on a data set and I've got to write a tool to do this analysis, I want to have some confidence that the tool is doing what I think it's doing, right? So yes, best practice is that we should test our software. You can't test it exhaustively, of course. But you should always have maybe 1 or 2 test cases where you know what the answer is going to be, you know what the output should be, and you can check that it is giving you what you expect it to be giving. Okay. I know it probably sounds kind of rudimentary, but it's important that you say this stuff explicitly. So, with respect to planning, what does planning usually look like in practice? I can tell you that if you were to get a computer science degree, you'd have to take a course very early on, probably on programming logic, and you would spend most of that course writing what we call pseudocode, and you'd be drawing flowcharts, right? Regardless of the programming language that you're going to finally implement your code in, planning doesn't care about that, right? Planning is you writing down the plan. So pseudocode lets you quickly write out code in your own words, how you would normally talk to somebody. And a flowchart allows you to draw out the flow of the program and how things are interconnected, right? It gives you a blueprint for what you're going to actually implement when the time comes. Now, to use pseudocode, you have to know about this idea called control flow. Control flow is you controlling the flow of the processing in your program. I think it'll make more sense when I show you some examples of it, instead of me defining it with the same words that its name, right? It's a poor way to define something. Let's look at flowcharts first here. So these are some basic shapes we think about when we do flowcharts. And don't get me wrong, guys, I make flowcharts all the time. I do not adhere to this necessarily, right? If it's just a flowchart for myself or a flowchart to show somebody else quickly, who cares what shapes I use, right? But if you want to be technically correct, there are designated shapes for designated things, right? So typically, we'll use ovals or circles to represent terminal portions of the program. That is the starting points and ending points. Right? We'll use rectangles or squares to represent processes or functions. We'll use parallelograms to represent input and output of the program. Are we reading from a file? Are we printing to the screen? Are we reading from a database online, right? These are the sorts of things that constitute I/O, input and output. And then we have our diamonds, which typically represent conditional statements, which we use for decision making. Okay? Pretty straightforward. And again, when I use these, a lot of times I typically do like to use like a different shape for beginning and end. And then as I go through, I put most of the things in a process box generally. But depends on how technically right you want to be when you make your flowchart. It's up to you. So here's an example of a flowchart for when I wake up in the morning. I start my day. I look at the time to get up, make an espresso. That's the end of my little routine. If it's not time to get up, I go back to sleep, right? And then I repeat this, check the clock again and go through. So simple flow chart representing an algorithm. Easy enough? Okay. So the control flow is the order in which we're going to execute each individual instruction, right? So it's the control flow in this example that allows me at this point to decide if I'm going to either go back to sleep or if I'm going to make that espresso. Talking myself into wanting an espresso right now, actually. So When we're using this control flow, which programming paradigm are we in? Are we in that declarative or the imperative one? We're in imperative, right? We're controlling the flow. We're telling it how to do what we want it to do. Absolutely. Absolutely. Good job. So there's a couple types of control flow that you should be familiar with. All programming languages that are sequential and object-oriented or imperative in nature have all of these forms of control flow. Okay, so this is abstract of any specific programming language. All of this knowledge is ubiquitous across the board there. You can have sequential. Probably know what that is off the top of your head, right? It's literally just line 1, line 2, line 3, line 4, but you got to define it. We have selections and we have iteration. Not too much to worry about here. We'll take a little look at each one of these, and I'll keep going with my little morning routine thing here. So a sequential example, this is written in pseudocode, so now you're seeing what pseudocode might look like. Turn on espresso machine, grind espresso machine, or grind the beans, pack the portafilter, pull an espresso, drink the espresso. All right, that's the algorithm. That's how you would normally make an espresso. So this is all sequential. 1, 2, 3, 4, 5. Easy now. We'll look at selection. We have a couple keywords that tend to show up everywhere. And we typically refer to these as if-else statements, right? You can use an if by itself, but if you have a couple things, you can use an if, else if. You can even end it with just an open-ended else that catches everything else that you didn't consider, right? And so if we think about this, how might I write this in pseudocode? How could I use this? Well, I'm going to expand that part about grinding my espresso beans, and I'm going to make a decision here. Is it late? Well, if it is, I think I'll use decaf. If not, I'll go ahead and grind up some regular espresso, right? This is an easy way to use a selection criterion or a conditional statement, as we like to refer to it, to control the flow in your code. You can also look at iteration. Iteration is another process we're all familiar with. It's just doing something over and over and over again, right? That's what iteration means. And so here, after I pull that espresso, I want to drink it. I guess I could take it like a single shot. I do that sometimes. But more than likely, I'm going to sip my espresso. I'm going to drink it by repeatedly taking little sips, right? And so this is an example of me writing out this algorithm and showing you an example of iteration in pseudocode. You can probably see that it doesn't take much. The ability to make a decision, to fork one way or the other based on that decision, and the ability to redo something repeatedly pretty much allows you to overcome most problems. Right? You can design an algorithm using these operators to pretty much overcome any problem. I don't even know if you could think of one you couldn't. So pseudocode is a great way to outline your algorithm, to outline your program. Here, I put it all together for you with these little examples as we expanded it going through. This is what it looks like. This is pseudocode, but technically it could be a little bit more proper. And what we do to make it a little more proper is we actually use these operators. We use these terms that would be in your code. So here, you notice instead of just saying, is it late, I've added if it is late. This better represents how I'll actually write the code, right? Here, I've added while. While is one of those keywords in a lot of programming language that tells the program you're going to do iteration, okay? So this is what you want to think about when you're thinking about pseudocode. You write down what you would like the program to do in natural language, and that gives you a strong outline for what you're going to actually implement using programming. Okay? So before we can really start implementing our code, there's a couple more things that I really want everybody to be aware of, okay? And that is that programming languages have intrinsic data types, as we call them. Intrinsic means inherent, built in, right? They have intrinsic syntax and semantics. Think about it this way. if you speak German and somebody else speaks Russian, they can both communicate the same ideas, right? But the structure of the sentence that they write is going to be different. Maybe the ordering of the words is going to be different. And the actual words they use, because they are different languages, are going to be different, right? But the meaning can be interconverted between the two. The programming is going to give us that same ability. That slide's a little bit further down. We'll come back to that part. So we're going to go to the data types first. But this is the idea with syntax and semantics and data types, right? The choice of programming language should really come from two things. One, of course, if you only know one programming language and you don't want to learn another one, you better just force it to work in the language you know. But the best practice, and what my answer would be when someone asks me, Guy, what language do you code in? I always say I code in the language best suited for the problem, right? I'm not going to try to do statistical analysis in Fortran. I'll do that in R. I'm also not going to try to write some fancy mathematical integrator in R. I'd write that in Fortran. So understanding the strengths and the purposes of programming languages can help inform your decision. And you'll probably find throughout your career that you can rely on one or two languages to really accomplish most of your workload. You just stick with them, get good with them. They'll take you far. So let's talk about data types. Try to recollect for a minute my little analogy of water towers, okay? And how these water towers represent real things, the transistors inside of your computers, okay? And let's discuss how a computer actually has a sense of what a number is or what a letter is. How is the computer actually storing our data? All I've told you at this point is that you have an orchard of transistors, so to say, and that these things can either have a charge or not have a charge, right? These apple trees can have apples on them or not, however you want to look at the analogy, okay? Well, we can map what we're seeing to some definitive symbol that we want to represent. So here's an example. The integer 100 is represented in binary as 0, 1, 1, 0, 0, 1, 0, 0. Okay? I'm sure you guys have heard of binary before, and most of you know good and well that the zeros and ones that we deal with computer science come from this idea of operating in a binary world. Well, this is why. This is why we have to use binary numbers, because we either have something in our water tower or we don't. Zeros and ones. Binary is extremely convenient for us to represent any number in a format that we could encode with a set of transistors, right? That's what we're going to do with it. And so in this particular case, if I want to represent this number with a set of transistors inside my computer, it could look something like this, right? Where a shaded circle represents a 1, and an unshaded circle represents a 0. Okay, cool. Well, hold on a minute. What if I want to represent negative 100? Then what do I do? Right? Okay, well, how about we add one additional transistor, and we always acknowledge that that one transistor, if it's on, it's a negative sign, and if it's off, it's not. Easy peasy, right? So here's a good example of that. Now, I didn't tell you it was already up top here, but it was. And here, I've just shaded it in to represent that we're saying this is a negative number. And what we would refer to this technically in terms of data typing is I would tell you that this is a signed integer. So if you ever see this terminology about being signed or unsigned, what that's telling you is if the number can accept negative values or not. Let me ask you guys this question. What might be the benefit of using an unsigned integer? What does that do for me? Any guesses? That's okay. I wanted you to think about it for a minute. Consider I have a limited number of transistors. If I didn't have to use this one for plus and minus, I can represent binary numbers with an additional digit. Can I not? So let's say the maximum number I can represent with 9 binary digits is something like, I'll just give you a fake number, 200. The moment I try to represent 201, I can't store it there, right? I would need additional transistors to be able to represent that number. Oh, if it's an unsigned integer, I can store a larger magnitude number in a smaller section of memory. That's why that kind of thing comes about, okay? Now, of course, there's other data types. It's not strictly just integers. And so here's the common data types that you guys should all be familiar with, at least in terms of the names of them and loosely what they represent. Integers are simply whole numbers, positive or negative, 0 included. These are your integer values. Floating point numbers are your numbers that include a decimal in them, period. Right? So if I give you 1 and I give you 1.0, they're both the same number numerically speaking, right? They're both 1. However, 1.0, in terms of how we represent it and store it and work with it on the computer, is not the same as 1. Because we have to make sure we can store that decimal and that we can store the trailing digits behind that decimal place. There's a little bit of mathematical work that goes into doing that sort of thing because of the way we actually represent fractions on a computer. It's not very straightforward, and I'm not going to go into the details of that. Of course, there's characters. We like to be able to type letters on the screen, right? It's nice that, you know, everything on a computer isn't just numbers, there's letters. So we can represent characters. If we put a bunch of characters together, we refer to that as a string. Okay? And then finally, there's a data type called the Boolean. Oftentimes, when you're thinking about Boolean values, you're thinking in terms of true and false. Easy enough. So this is it. These are the common data types. There's maybe more data types depending on certain languages and what you get into, but you'll find these data types in just about every single programming language that exists. Well, how exactly do we represent these non-integer values? How do I represent the letter A, for example? I told you how I can do a number. I just convert that number to binary, right? And now once I've got that number in binary, boom, I lay it out on the transistors. How might I do this with characters? Any guesses? Binary is definitely in there, but how do I get to a binary representation? Can you think of a way I might accomplish that? What's that? I can't hear you. Sorry.
I said except decimals.
Except decimals, yeah. Well, decimals are there too, but I'll just give you the answer. Let's look. Well, we encode the data type along with the value, right? So I hinted at this with the signed and unsigned. How I'm going to dedicate so many transistors to storing a value and one additional transistor to reminding me if it's a positive or negative number. So now, why don't I add an additional 1 or 2 or 3 transistors that I always look at first. And when I look at these 3 transistors, based on if it's a 111, 101, whatever the pattern is, that tells me if I'm dealing with a character, Boolean, an integer, or a floating point value. So now I've looked and I know how to interpret the other part that I'm going to look at next, right? Here's an example of this. If we only have 4 intrinsic data types available to us, the integer, the floating point, the character, and the Boolean, we could represent all of them with 2 bits, which is with 2 transistors on our system, right? Does this make sense? So now, if I expand out what I showed you previously about the number 100, this is what it would really look like. You have some bits dedicated to encoding what the actual data type is. 1 bit dedicated to encoding if it's a positive or negative value. And then some number of bits large enough to capture the entire value in binary. Right? Cool. pretty straightforward, I think. I know it's a lot and we're diving into it, but I think each tiny step is pretty straightforward as we move through it. Consider a Boolean value. Similar thing, right? Now, I need 3 bits. The first 2 bits tell me that this thing's a Boolean, and then all I need to do is look at the 3rd bit. Well, if it's on, I've got true, and if it's off, I've got false. Okay? Let's look at another example. Letters, characters, right? This is what I was trying to see if you might think about here. Is we map them. We map the characters to numeric values. And we say, hey, let's say A is equal to, what did I put up here? 0. And capital A is equal to 27. Well, if there's 26 letters in the English alphabet, I can represent all of the letters in the English alphabet, lowercase and capital, right? With 52 numbers. Now, as long as I know what I'm interpreting is supposed to be interpreted as a character, I won't read it. I won't read it and tell you, hey, here's 27, right? Instead I'll hand you an A, because I know I'm interpreting a character here, not a number. So pretty straightforward. I hope that wasn't too much. I really love to give that level of talk because I think a lot of people miss out on making the connection that computers aren't magic. Something very physical, something very real is happening inside the computer. And there's a very logical way to understand how what you're programming is interacting with the hardware itself. This is how, right? The lower level programming language that you're going to be using, the more you have to think about my little water tower analogy. The higher level language you use, let's say you're using something like Python, you hardly ever have to think about it, right? So I think I mentioned earlier, I finished that off by saying there were intrinsic data types, intrinsic syntax, and intrinsic semantics. So let's just define real quick what I mean by syntax and semantics. Syntax is the way that the language describes its characters to comprise a valid program. In other words, if I want to write, let's say, a conditional statement, I want to make a decision. In C, I might need to wrap that decision in parentheses. In Python, I may need to put a colon at the end of that line to signify what it is. Logically, I'm doing the same thing. I'm making a decision. But the syntax, which is dependent on the language, is different because it's just what Python or C or Ruby or whatever language I'm using demands of me. It's how it expects things to be written. Now, the semantics, on the other hand, tells you how to interpret what you're reading. It's how to kind of understand what the code means. And oftentimes, people don't really worry too much about semantics. But here's an example I put up here to kind of differentiate the two for you succinctly. Colorless green ideas sleep furiously. What the hell does that even mean? Right? This sentence is syntactically correct, but it has no meaning, no semantic value. Okay? If you really break this down and you think about it in terms of English, there's nothing wrong with this sentence, except for the fact that it has no meaning. This is the difference between syntax and semantics. All right? Now let me show you a hard example here. Let's use C and C++ and Python in this particular example. So it should already be assumed that the language differs from language to language to language. The syntax and the semantics is probably going to differ from language to language. But you'll actually find in a number of languages, there's a lot of similarities. Or maybe they're just straight up the same. What's going on there? In the case of something like C versus something like C++, we look at these two programs. These are all valid programs. These all do one thing. They print what's up to the screen. All right, you could write these right now and run them. They would all run for you. And you'll notice that as you compare my C to my C++ version of the code, the only part that's different is this line, which if you didn't already infer, is actually telling the computer to do the print statement of what's up. The way I'm encapsulating that function is identical. The way I would provide parameters, identical. So what's going on here? Well, there's a number of languages that are derivatives of other languages. C++, C#, Python, Ruby, Java, JavaScript. I can go on and on and on. A lot of these languages are actually built on top of C. Someone took the C language, decided they wanted to add additional features, decided, hey, you know what? I'm going to invent object-oriented programming, and I'm going to set up C so that you can use C for object-oriented programming all the time. And then they wrap that thing up in a package, and they ship it off, and they call it C++. Or if you're Microsoft, you call it C#. Right? It's still C underneath, but there's additional abstraction layers that have been added by somebody. And because of those abstraction layers and the programmers not interacting now at the lower levels, the way you use the language is different. The way you think about the language is different. Okay? Then you have something like Python here. Well, Python's, maybe it looks a little similar, but arguably it's a lot different as well, right? Here, I've got curly brackets surrounding everything. Here, well, there's nothing surrounding everything. There's just a colon up top, right? My print statement, yet again, is different. But when we look at these three programs, we have to acknowledge that they are all the same program. They're all doing the same thing. This is why I really like people to focus on learning programming logic over learning a specific language, because learning that logic and understanding how to write the pseudocode and the flowchart means that to implement the program, all you have to do is look up how to do a conditional statement or iteration in the language of your choice now, right? Okay, so let's wrap up this little three-part of planning, implementing, and testing. Why do we test the code? Make sure it's working. Yeah, absolutely, right? And I just reiterate this because more often than not, we forget to do this. We're in such a hurry, we're in such a rush to get to the answer that taking a little bit of additional time to really vet what we've done and make sure that it's absolutely correct kind of escapes us, right? But it's always a best practice to have a test case and to validate your code, right? Nothing worse. I can tell you as a researcher, when you go back and you're analyzing data that took you 6 months to generate, and you find some bug in the code that you wrote 6 months ago that you used to generate that data, you've just lost 6 months of work because you didn't take an extra day or two to validate your code and make sure it was error-free before using it to generate all this data and do all this work for you. So real-world repercussions for not testing. And even someone like myself, I do this to myself every once in a while. I've been fortunate that I've got to the point where it happens far and few between, but even it happens to me. Okay. Testing gives the end user confidence. So if you're selling your software, if you're working for a company and you have those test cases, it gives who's ever downloading and using your software confidence that what they're getting out of it is going to be good. They might not have a chance to talk to you to hear that you tested this software. They're going to want to test it on their own to make sure that it's looking good. They're going to want to test it on their own to make sure that it was compiled on their specific hardware. Something with the machine level code didn't go awry and cause erroneous calculations to be made, for example. It could happen. It doesn't happen often, but it could happen. Always start simple with your test cases. No need to have exhaustive, extensive testing. A couple simple test cases is all you would need. And you can scale that up to the kind of thing you would expect in what we call production use, when it's actually put out on the floor and used for a bunch of stuff. So just today, I've been going through, I've been vetting some code that I rewrote last week. This code is going to be generating probably like 60 million lines of training data for an AI that I'm training. I had to sit there today and make it print out to the screen for me each individual component of just one sample, not all millions of them. I sit there by hand and verify that the numbers coming in, the numbers coming out are giving me exactly what they should be giving me, the math is good, and that the values are what are expected. Once that looked good, now I'm confident to generate a file with 20 million lines in it and to use that to train an AI, because I know that the data that I'm training the AI on is valid. Right? Okay. So we got 40 minutes left, and we might finish a little early. I don't remember how much I put in here. So let's go through some stuff here, because I think that if I had to pick two languages to teach somebody from the get-go, it would be C and Python. You guys know already I'm biased towards C. There's no getting around it. If you're with me, you're going to learn some C. But Python is an extremely powerful language, and I do use Python regularly as well. When I want to prototype something, that is, if I want to do something really quickly just to see if it'll work, I'll do it in Python. And once I see that it works, if I know that I'm going to have to do this thing over and over and over again, and that performance is going to become a consideration in my usage, I will then take the time after prototyping in Python to write it in a language like C, so that when I put it into production, I have the benefits of the performance gain. Okay? So very useful to know one of each. Okay? C. What an awesome language, really. So it's procedural, as I've already told you. The programs are compiled, which I already told you. High performance. I think I've already implied that over and over and over again. All of the things I love about C. Underpins numerous other programming languages, C++, C#, Java, JavaScript. A lot of these languages are built on top of the C language, which is really convenient, because when I'm writing C++, and there's something that I can do more efficiently with C, you can just write the C right in the middle of the C++ program. It is built on C after all. Very nice to be able to do that. The data types in C are what are called explicit data types. I'll have more on that for you guys in a minute. If you guys remember the last talk, I actually think I mentioned it back then. This language was developed to make the Unix operating system portable. They first developed it in a language called BCLP. BCLP was specific for that IBM PDB-7 computer that they were using. But in order to get Unix out and used by everybody, they invented C to be a machine-independent language, one of the first of its kind. And now we have Unix and Linux everywhere, right? Requires a main function. This is something that you just need to know as a programmer if you're going to get started with C. When you write a program in C, all programs are expected to have a main function. That's the one requirement. And as of 2021, it is the most popular programming language still. I think that's it. This is the face of the book that you can get that was written in '72 by Dennis Ritchie and Kerningham when they published it. So what does writing in C look like? Well, put up top here that they have to have a data type. This is what I mean by explicit data types. So look over here, and we'll take this one as an example. It's a function. The function's name is knock knock. It does not take an argument. That's what this part here means. It means there's no arguments being passed to it. And what this function does is it returns a string that says who's there. Pretty straightforward. Well, I have to specify what my function is going to return, what the data type of that return value is when I write in C. And so you'll notice I have character right here at the front. So this is telling my program that this function knock knock is going to give me back a string. Okay. Up top, I have the main function. The main function I have is an integer, because best practice is when the program terminates, it gives a number to the operating system. That number tells the operating system if this program executed as expected or if there was an error. It's nice to know if your program crashed or if it didn't crash, right? So I might return a 1 to signal that everything is cool, program terminated as expected. Otherwise, I'll return a 0 or some other number that specifies a specific error that was encountered, or just specifies generically that we executed with error. In a C function, you always specify the function name, followed by a set of parameters, any number of parameters you want. They're always contained within parentheses and separated by commas. And you put a block of code in between curly brackets. Do you guys have any questions about the syntax that I'm showing you right now? Let's see, did I say everything that I wrote here? Must have a unique name. They can't define 2 functions with the same name. That'd be crazy, right? Who would do that? Don't do that. The compiler won't allow you to do that. Functions with the void data type do not require a return statement. This is just some extra information. If you actually start coding in C, that's something to remember. I'm not going to hammer that into you right now. And the final thing I'll say, bringing this back to control flow, is that when a function is called in your code in C, the control flow moves into the functions block until it's returned back to where that function was called from. Does that make sense? Right, so I can have one function, and in the middle of my function, I can have my knock function. When you're thinking about it processing, you're thinking about it going sequentially through. Oh, it gets the knock, and now all of a sudden it teleports over into the knock function, marches through the bottom, and then comes back. It continues to go down where it was at previously. So all data types are explicit. When you declare a variable, when you declare a function, you always have to tell C what that data type is going to be. It wants to know up front. I think people should learn C as a first language, in part because of explicit data typing. It's important, if you ever want to troubleshoot and debug your code, that you understand the impact of the data types. They significantly impact your code. Consider if you have 5 transistors reserved for a data type, and you try to store a value in it that would require 7 transistors. What is that going to do to your code? I can tell you already that's the basis of hacking. Not all hacking, but that's the basis of hacking that can still be done today. It's called memory overflow hacking. You purposely place things in small segments of memory to push out and manipulate memory that you're not supposed to have access to, and then you can grab that data and look at it. That's why you don't want to give people physical access to your system. Okay. So I mentioned to you guys about doing selection before. So what does selection look like in C? Again, we also refer to these as conditional statements. So in C, we have if, else, else if. That's it. There's also a switch statement. I think I show it at some point, but this is enough to get you started. And I've got the examples over here. If condition, do something. These conditional statements always get evaluated, and they evaluate to either true or false. Obviously, if you get a truth, you enter into the code block and you execute it, and if you do not, you move on. You don't go into that code block. You can negate, as it's referred to, a conditional statement by putting an exclamation point in front of it in C. So a negation in programming is taking the opposite truth value. That's what it means. So when I write something like if exclamation condition 1, the way that I read this in terms of semantics is if condition 1 is not true, or if not condition 1. So typically for me, when I read code and I see the exclamation mark, I use the word not in my head. If not condition 1 and condition 2 or condition 3, then do something. Okay? You can do this for all sorts of things. You can say if x is not less than 5. Well, you could also say is greater than, right? Just gives you an example of how you can use these negation statements. And I did list on here for you guys, if anyone ends up playing around with any programming before I see you next, here's a list of the rational operators that are available for conditionals, right? So you can have greater than, less than, greater than equal to, less than equal to. Oh, what about this one? So when we actually want to compare two things in C, and we want to see if they are actually equal to one another, we use a double equal sign. Okay, and you might ask yourself, why? Why can't I just use a single equal sign, guy? And I'll tell you that because the single equal sign is reserved for assignment, right? If I want to say x equals 5, I need a way to differentiate assigning a value versus comparing two things to be equivalent to one another, right? And that's the reason. And then it follows suit that not equal is a negation followed by a single equal sign. Okay. Now there's also iteration, right? This was the other one I told you about, selections and iteration. So in C, we have really two ways to do iteration. We can use while or do/while loops, and we can use for loops. There's some subtle differences between the two of them, but the short message here is that either one is going to get the job done. The biggest difference when I look at these, just so that I tell you specifically what's going on, is if we start with something like while, which is the simplest case, while takes a single conditional statement. As long as that conditional statement evaluates to true, the code block will be executed, and then the conditional statement will be reevaluated. That will happen indefinitely until the conditional statement evaluates to false. Then control flow will return back to the function that called this. If I have a do loop, the only thing that's different about do is that do always does the thing before it checks the conditional. Subtle difference. That's all. That's the only difference. You put what it's going to do before checking it. This is important in the case that you always want to do something at least once. Maybe you want to do it a bunch of times, but you want to do it at least once. So you do it, then you check the conditional, and if it's true, you iterate. For loops can be used identically to a while loop, and that's what I'm showing you on the top right here. Now you'll notice, if you look carefully, I've included semicolons around this condition. If I write a for loop like this, I use for instead of while, semicolon, my condition. This behaves identical to a while loop. So then the question might be, what's the purpose of a for loop then? Well, here I'm not doing anything, but down here I can actually specify instructions what to do when I initially enter this loop, only do it once, and every single time I come back into the loop, is there something I want to do? Let's think about an example of why I might want to do this. Let's say I want to print the numbers 1 through 100. Right? I could say for x equals 1 if x is less than or equal to 100, x plus equals 1, or x equals x plus 1, right? And then here I can have a statement that just says print x. Now I can achieve the same thing with a while loop. I just have to specifically put within my control block the declarations and the if statements and stuff like that. So a lot of people will just use fors for everything, but I think there's certainly a place for whiles as well. It can kind of be a personal preference in your own style. So here I'm just kind of laying out the syntax for you. Here's an example of using the for loop, only instead of counting 1 through 100, I'm doing 99 bottles of beer on the wall. And this is an example of what that might look like. This is real functional code. If you try to write this and implement it, it'll compile and run. This is a demonstration of a flow chart for a for loop. All right, so I've introduced you guys to flow charts now. This should make perfect sense. You encounter the for loop, you execute the init block, You check the conditional. If that conditional is true, you execute its code block. You increment whatever's in the increment portion. In this case, I'm decreasing the number of bottles of beer. Check the conditional again until you get a false value, and then you move on. Finally, have an example here of how you guys could write your very first C program if you've never written one before. This is a simple hello world program. It's classic. Anytime you're dealing with the first case example of programming, typically it's a print to screen kind of thing, where just print something onto your terminal or into your console if you're using like Visual Studio. And this is the full code for a C program that prints hello world. At the very top, I'm showing you something I haven't shown you before, which is an include statement. So this is how I would include header files or libraries that are stored on my system or that I've written myself. Right? It's never very good. I should say perhaps it's frowned upon to write monolithic code. When I say monolithic code, I mean, who wants to open a file with 20 million lines in it? I don't. It's better to partition things off into separate files and to encapsulate them in ways that make sense so that it's manageable for a programmer. Just because a lot of programs we write are small, we break all these functions off into we break all these operations off into functions and abstract them away. It would make sense that if my code has become so large that I might put things in certain files where I know, hey, I keep all my math functions in my math file, right? I keep all of my file input and output functions in my IO file, however you might want to store it. Once you've written this into a file, and you guys should be able to do this, especially if you have a Mac, you could do it right now. You could probably do it on the command line in Git Bash on Windows. You can use the GNU compiler, which is a free compiler pre-installed on most pieces of hardware nowadays. And this is how you compile the program. You give it the name of the C file, .c, and the output name for the actual name of the program that you want. This is going to produce an executable called hello. And you can execute it on the command line by doing ./ in the name of the program. If you type this and hit enter, you'll see it'll say hello world. Or if you change the print statement, it'll say whatever you want it to say. So let's look at Python as a counterexample, right? That was C. That's how C does things. Explicit types requires the main function, has to be compiled, right? Well, what about Python? It's an object-oriented programming language, as I mentioned before. Its programs are interpreted instead of compiled. It's really good for fast development time. Indentation dependent. My least favorite thing about Python is the indentation stuff. White space in a programming file are things like tabs, spaces, and enters when you move to a new line. Those characters are hidden from us as a user. You don't want to see a bunch of /ns and stuff like that because they're hidden characters that tell us to put white space there. But they're there, and they're seen by the interpreter. And Python knows the difference between a tab and a space. So even though I'm looking at a block of code and all the letters start at the same place, that doesn't mean one doesn't have 8 spaces and the other one has 2 tabs. Python will yell at you and complain and not let you run your code until you make them all the same. I just hate that. Anyways, it's not that old of a language. It was released in '91. Unlike C, the data types in Python are implicit. Remember, I told you Python's good for fast development. This is one of the reasons why. No main function is required. That should make sense. Why don't I need a main function in Python, but I need one in C? Absolutely. C is compiled. C has to have an entry point for executing the instruction set. Python is interpreted top to bottom. So it doesn't need a main function.
But I guess like in some cases like people include the name if name equals main thing.
Yeah.
Because Python is both as both the compiler and
No, it's just a way to mimic another language. So it can be really nice to think of a main function as being your entry point. And what you'll see in those codes is that they'll define that main function. And so everything in the whole Python script or program is a function except for one line at the very bottom, which calls the main function. Yeah, good catch. Third most popular programming language as of 2021, continuing to grow. Continuing to grow. Just like C, your functions have to have unique names. I mean, you're going to see this everywhere, right? You got to have unique names. You can't tell the computer that pink means 5 different things. It's not going to accept that, right? Functions can have any number of parameters, just like in C. Unlike C, in Python, though, your function can return multiple things back to you. So in C, when a function returns control, it can only return one thing as it returns control. It can return a single number, a single string, something like that. But with Python, I can have a function that returns a string and a number, or 5 numbers and a string and an array. So again, convenient, fast for prototyping, fast for getting up and running with. So here we have when a function is called, control is given to the same. This is the same. This is typical control flow, right? If I see a function being called in the code, and I'm really trying to read the code and understand it myself, I need to stop. If I don't understand that function, and go read that function's code, because that's how the code is actually being processed. And the other thing that's nice about Python that you don't have in C is that your parameters can have default values. When you have a default value on a parameter in Python, you can call that function without defining that parameter, and the default will be used. If you have a function in C that requires a parameter and you don't pass it a parameter, the code will not compile. Okay? So I've written a couple of examples up here, just like on the other one, to just break everything down. You can see that up here, there is no type. Technically, using DEF in Python is a type because you're specifying that you're writing a function. So it's still appropriate to write the way I wrote it. But you'll notice I'm not saying that this is a character or an integer. I'm just saying, give me a function with this name. Also, my parameter doesn't have a type. I'm just telling it I have some parameter called name. And here, just more examples. This one, I'm actually returning 2 values, right? I'm returning the first name and the last name. You do that by separating them with commas. And here, I'm showing you an example of a default value, where unless you specify a number of repetitions, the default will be 100, right? A lot of these examples I provided to you guys in these slides is so that if you want to go off and try to do a little programming in C or Python, you have a solid reference for all the most important things you need to know to get up and running and writing your own code, okay? So that's why I've kind of hammered these things in here for you. Don't feel like you have to, but if you want to, this is going to be a good resource for you to get started with. Importantly, these data types are implicit. I'm just going to hammer this home again. C has explicit data types. You have to tell C every single time. That means you have to be aware of the data types you're dealing with. In Python, you don't. You don't even have to think about it. But you should. And I tend to tell students who learn Python as a first language that they had a little bit of a shortcoming in doing so, and that's that they've been never forced to think about data types. When you're trying to troubleshoot and debug your code, you have to think about these things, even if they're not explicitly written there. And I can remember students writing code, and they were trying to print functions instead of printing values. And they'd call me over and ask me, hey, why am I getting this error? And I'm like, well, look at the print function. What's its argument? Its argument is a string, right? And they're like, yeah. I'm like, okay, what are you trying to print? oh, they're printing a function. They're not printing this. No wonder it's not working, right? So not thinking about the data types sets you up for frustration. It sets you up to hit a wall and to probably maybe give up if you don't have enough encouragement to keep pushing through and figuring out what's going on. If you find yourself in that place, know that if you're dealing with Python, you probably need to think about the data types. Okay. We're going to look at the exact same examples that I gave you for C. In this way, you guys now have a slideshow you can look at that gives you a direct comparison between the two. And all of the code that I've written when it's real code is real code. You can use it and manipulate it however you want. So just like in C, we have if, else, and else if statements. You'll notice the syntax is different though here, right? Here, instead of actually writing else space if, in Python, it's a single word, elif, with no space. You'll also notice that I'm no longer putting curly brackets around my blocks of code. In Python, a block of code is designated by common indentation. So as long as everything is indented at the same point, it belongs to the preceding text that is not indented that far. That's how it works in Python, which is why white space can be annoying. Loops, just like in C, you've got while loops and you've got for loops. And you'll probably find that in most programming languages, you have these things. If, else, else if, for, and while, really quite ubiquitous. It's hard to come up with other names for such operations, right? And if you want programming logic to be ubiquitous, you need to have programming logic to be ubiquitous. What's up, Sam?
Does the same indentation matter in the group for C++ or C?
No. C++ and C, they rely on the curly brackets to determine what belongs to what. So in C, you could put everything on one line if you really wanted to, and it would compile and run just fine. In practice, you should never do that. It's going to be terrible to look at and try to read. So no, in C++, it doesn't matter at all. In Python and in languages like Python, Ruby, for example, these things do matter at times. For is a little bit different, right? Unlike in C, where I have the initial and the increment thing, for is a little smarter. I can do something like for x in range, and it automatically declares this variable x for me, automatically assigns these values as I go through. Again, great for prototyping, great for getting up and running for rapid development. And if you don't have to use it millions and millions of times, great for production too, right? Because you're able to develop it so quickly. Oh man, look how much easier our hello world program is in Python. It's literally one line. Print hello world. Now you could type that into the Python interpreter and get an immediate output, or you could write it in a Python script / program, which we typically write as .py. And you could call this by passing it to Python, and you'd see it being printed to your screen. Do you guys remember from the last talk when I told you about file extensions? If I named this file, hello, guy is so awesome, would it still run? It absolutely would. File extensions are just for us to look at. The code contained in this file is still Python. So when the Python interpreter sees it, it's going to interpret it. It's going to run it just fine. If I write my C code and I put it in a .py file, the compiler doesn't care what the file extension is. I'm specifying the files to it. What it cares about is what is inside of the file. So there's conventions, which is why I'm mentioning that when we write Python in the script, we tend to end it with .py, but that doesn't mean you can't put your own extension on there if you're differentiating. Maybe you're writing code that's specific to Python 3, and you want an easy way to remember, so you name them .py3. That would be completely acceptable. Nothing wrong with that, right? It's why when I write shell scripts for Unix to automate things, I end them in .sh. It's a convention. It's not required. You could also write one .csh if it was specific to C shell, if you really wanted to. Doesn't matter. That's about it. So we've got 10 minutes. I can answer some questions for you guys. I could also show you a sneak peek of the exercises that I'll be giving you next semester in applied bioinformatics. And maybe even take a vote if you guys would like them. I'll share those exercises with you now so that you could take a crack at them in advance if you don't want to wait. So I think we'll do that because we've got 10 minutes. It'll only take me 5 minutes to show you these exercises, unless PowerPoint crashes 1,000 times on me, which seems to be the thing for today. Okay, I'll just scroll through it. That way it can't crash. So we can just jump up to part 5. Okay, so this is what I'm going to be challenging you guys to do next semester. And I think that the exercises I've developed for you herein really set you up for success. When you think about bioinformatics, when you think about data science more generally, your job is to take data contained within files or on the internet, which is arguably still on a file, just on somebody else's computer, right? To be able to look at that data, do something with that data. Oftentimes, it's going to be a pretty routine operation. You're going to maybe filter it, maybe sort it, maybe perform little mathematical operations on it, like take an average, something like that, right? And then you're going to want to do something with the outcome of your analysis. You're going to either want to write a new file with it. You're either going to want to make a plot with it, show data point, right? And generically, that's kind of the whole pipeline. You're always going to need to acquire data, do something with that data, and show that you've done something with that data. And so the exercises here are always to write pseudocode for each assignment, to write a flowchart for each assignment, and then to implement the assignment in C and in Python. And that's important because I want you to see that there are benefits to both. And I want you to see that once you understand the programming logic, the subtle differences of picking up a little syntax and going back and forth between C and Python really isn't a big deal. You can definitely handle it. I know you guys can handle this kind of stuff. So let me show you these 3 activities that I have. This is a little instruction set, like I said. Flowchart, pseudocode, implement in C, implement in Python. And the first assignment is to do these hello worlds. Well, I've already shown you how to do a hello world on the screen, right? But if you haven't done it yet, that's where you start. Simple program. If it's in C, it'll be your first time compiling if you haven't compiled before. Once you accomplish that, part 2 of this activity is to write it to a file instead, right? I want to give you that experience of opening a file programmatically in that file. That way, no matter what you have to do in the future, you know that you can at least open a file and write it to a file to use later on, right? I'm going to give you a little experience using conditionals and using iteration all at once. I'm going to challenge you to create, as I say, 10 different worlds, printing it just to the screen. And what the output is supposed to look like is hello, first world, second world, third, fourth, fifth. And you can see how maybe you got to think about a couple things here. How do I successfully get ST and ND and TH on the right numbers? Conditional statement would let me do that, right? A loop would allow me to go over these 10 worlds very easily, right? So I think if you've never coded before, these seem like pretty decent challenges. But in hindsight, when you get through these activities, you will have developed some really important skills that are foundational and really powerful if you're good with them. Even though they're simple and there's not a lot to them, they can be very powerful. Now, don't worry, I do provide all the answers in the activity as well. So this is beneficial if I give this to you early and you want to explore and push yourself, all the answers are here as well. My example of the flow chart, my example of the pseudocode, pretty straightforward. And the code written out both in C and in Python. Now, when I send this to you guys, do yourself the favor of trying to write the code without looking at my code first, right? Don't fall into that trap. It's just like mathematics. When you're in lecture and your professor is going through the math and you're like, man, I followed it. Yeah, I got it. And then you sit down to do a problem and you're like, whoa, I can't do this at all. It's a lot easier to follow than it is to do when it comes to things that are rational and logical like math and programming. You'll learn more if you fail, as funny as that sounds. How many of you guys missed a question on a test one time and then you went back and looked and you're like, oh, I missed it. And now like you'll never forget that that is actually the right answer. You only have that knowledge because you failed and went back and looked. If you would have looked up front, you wouldn't have anchored that knowledge. Okay? So resist the urge to look up front, try to write it, go back in the slides and use other examples. And then once you finished it, compare it to how I wrote it. Activity 2, sorry, not part 2 of this one, flowchart, pseudocode again, code again, so on and so forth. It's all laid out for you. Activity number 2, what's this one all about? Here, I'm going to have you take some number of inputs, compute their average, print it onto the screen. You've already been printing in activity 1, so we're just building a little bit into this. Now, I'm asking you to actually do something with some data, right? You're moving more towards data science here. Something as simple as taking an average. But hey, at the end of the day, when you're dealing with manipulating numbers, all you're ever going to be doing is loading numbers and doing something to them mathematically, right? So if you can load a bunch of numbers and take the average, you can load a bunch of numbers and do anything mathematical to them, right? Pretty straightforward. The second part is instead of having the user input the numbers interactively, you're going to read them from a file instead. So now for the first time, I'm having you actually read from a file, not just write to a file. You're going to have to compute the average, print at the screen, and then I'm going to challenge you to compute a running average and write it to a file. If you don't know what a running average is, that's a great time to take a moment and Google it. Really, all it is you look at one, compute the average, look at the next one, compute the total average. Every time you take a step, you compute a new average that has more elements in it, right? That's the running average. So I'm just challenging you to do a little bit more with the data in this case. And now, after you've been successful with activity 2, you now know, both in Python and in C, how to open files, read data from a file, how to do something with that data, and then write it back to a file or print it to the screen. You can do either one. You could also write a program that would just let a user type numbers in and use it. So 2 ways to get data in, 2 ways to get data out, printing it or writing it to a file. Really powerful, right? Because everything else you're going to be doing is in the middle. That's it. So again, I've got all the actual answers up here for you guys to go through when you look at it. All the code works. You could copy and paste it if you really wanted to, but again, avoid that pitfall. Challenge yourself up front. It'll pay off. And then this is the final activity. A little more advanced. Filtering and sorting, as I call it. So here, building off of activity 2, we're going to read a group of values from a file, and we're going to compute the average, but only on non-zeros. When we're done, we're going to print the answer. So I'm just complicating it a little bit, right? I'm just telling you that as you're computing that average, you need to check if you're dealing with a 0 or not, and if you are, ignore it. This could be important, right? Maybe you're computing something with a data set, and you're only interested in values that are above or below a given threshold. There's a great application for something like this, right? Oh, I'm only interested in patients that have this many single nucleotide polymorphisms. And if their data set doesn't show that, I'm going to ignore them in my analysis. Good example, right? And part 2 here is you're going to read values from a file, remove the negative values from those that you read in, and then you're going to write everything that's left over in descending order. So here I'm having you actually kind of filter out things and then to reorganize and sort that data before writing it to a file. So each one of these is designed to take you very quickly from somebody who's never programmed in C or Python and putting you into a position where if you're strong with these three arguably rudimentary activities, there's not much you won't be able to do in terms of data processing on the command line with your own original programs in C or in Python. This also means if you're downloading a tool that's pre-written and is open source, you'll have the ability to open the source, to read the source, to modify the program to suit your needs, so on and so forth, which is a really great thing to be able to do. So I think I already talked myself into it, unless you guys tell me not to bother giving you this PowerPoint. Any of you guys think you'll actually try? Awesome. So next semester when I see you, this will be our first talk again. I will briefly go over all of the lecture from today, probably in like a 20-minute recap since you had it all today. And then we'll spend most of that first lecture doing the practical. So those of you that don't have an opportunity to practice this before then, you'll have an opportunity during that class. For those of you who do try before then, you'll have an opportunity to really shine and show that you can get through them quickly and implement them quickly and ask questions while I'm here for you. And that's what we'll do for that first class next time. Cool. Any lingering questions? Are you guys finding the more computer sciencey stuff beneficial? Are you still interested in this kind of stuff? Unix and the programming? Yeah? Awesome. Well, thanks.